Okay, take roll. All right, Amo, Bessie is here. Bishop, here. Greg, Claudio. Claudio. Oh. Chestnut. Here. Fullwood. Here. Erlinson. Here. Gerard. Green. Kennedy. Leonard. Mohammed Boy is here. Spall. Sullivan is here, and Swiss Stack is here. All right. So we're going to move on to chapter 8. But before we do that, I want to harken back on something that I talked about in the latter part of chapter 7. So I'll be going back to this slide right here in chapter 7. I'm sorry about that slide. This one. Okay. So if you recall, when I was going through the discussion of the different types of orbitals that are present in the different shells, and I showed you this, we showed you all the different types of orbitals along with their respective quantum numbers up to the third shell, and we can actually, based on our understanding of the rules, especially with respect to the quantum numbers, we can basically extend this particular table to higher shells, right, the fourth and fifth and so on, all right? So just to recap a bit, the summary of this is that in the first shell, there's only one orbital, and that's the 1s orbital. In the second shell, you have two types of orbital. You have the 2s orbitals, which are spherical in shape, and then you have three 2p orbitals, all right? And then when you get to the third shell, you have the 3s orbitals, you have three 3p orbitals, and you have five 3d orbitals, and so on and so forth for the fourth and the fifth and the sixth and so on, all right? So basically, these are the orbitals, and also let me remind you that the energy of the shells increases starting from the first to the second, right? So this is the lowest energy shell, the first shell, and then the second shell, which contains all these orbitals, will be the next in line in terms of energy, and then you have the third and fourth and so on. All right, so that's important for us to understand so that we can appreciate what we're going to discuss now in chapter 8. So let me go to chapter 8, and chapter 8 now is where we deal with electron configuration and how it relates to how the atoms are arranged in the periodic table. So we're going to talk about what electron configurations are, but basically it's a way of representing how the electrons are distributed among the orbitals. Now, in order for us to understand that, we have to understand how the orbitals are arranged in energy, because it turns out to be a bit more complicated than just simply looking at the energy of the shells. So the diagram I'm going to show you here is a comparison between how the orbitals are distributed in the case of the hydrogen atom compared to a multi-electron atom like helium and other atoms, right? So let's focus on this side here. And basically what you'll find is that, okay, the orbitals are located within their respective shells. So you have the 1s orbital here in the first shell, and then you have the 2s and 2p in the second shell, and so on and so forth. And what you'll find is that in the case of the hydrogen atom, and let me just say, not only the hydrogen atom, but pretty much any structure that has only one electron, all right? What you'll find is that in the second shell, the energies of the 2s and 2p orbitals will be the same. In the third shell, the energies of the 3s, 3p, and 3d orbitals will be the same. And the same will be true for the 4s and so on. I mean, for the fourth shell and so on. So basically what I'm saying here is that within the shell, for the hydrogen atom or any one electron structure, the orbitals, all the orbitals will have the same energy, all right? Now, when you get to a typical multi-electron atom, two things are different, right? The first thing you'll notice is that the energies of the shells will be lower in the case of the multi-electron atom. So for example, the first shell, which contains a 1s orbital, here, this is the energy level here. Then down here is what will happen in the case of the multi-electron atom. So the energy of the first shell will be lower than the energy of the first shell here in the case of the hydrogen atom. And the same is true for all the other shells. So this is the second shell, which contains the 2s and 2p orbitals. In the case of the multi-electron atoms, as you can see, the energy of the 2s and 2p orbitals would be lower compared to the case of the hydrogen atom, all right? And the same is true for the third shell, fourth shell, and so on. Another important difference is that within the shells where you have different orbitals of different types, you're going to have a splitting of the energy. In other words, the energies of the orbitals will not be the same when you're talking about orbitals of different types. So in the case of the hydrogen atom, for example, the 2s orbital will have the same energy as the 2p orbital, right? But in the case of the multi-electron atom, what you'll find is that the 2s orbitals will be of a lower energy compared to the 2p orbital, right? And the same is true for the third shell. These are the orbitals, 3s lower than 3p, lower than 3d. And in the case of the fourth shell, the 4s will be lower than 4p, which will be lower than 4d, which is not shown, which will be lower than 4f, which is also not shown, all right? So that's the big difference between a one electron structure like the hydrogen atom and a typical multi-electron atom. There are two differences. One, the shells, in terms of their energies, would be on average lower in the case of the multi-electron atom compared to the hydrogen atom. And within the shells where you have different orbitals of different types, there will be a splitting of the energies where the energies will not be equal for the different orbitals of the different types, all right? So that's basically what happens in the case of the multi-electron atom. So this kind of complicates things because it kind of makes things more difficult in terms of determining how the orbitals are arranged in energy, especially for the orbitals in a higher shell. Because, for example, what you'll find, and we're going to discuss that later on, you'll find that the 4s orbital, even though it's in a higher shell than the 3d orbital, its energy will be lower compared to the 3d subshell. All right, and there are other such discrepancies that exist as you move up in energy for the different orbitals, for different shells. All right. Okay, so let's talk about electron configuration. I think I mentioned it before. The electron configuration is basically a description of how the electrons are distributed within or between the orbitals of an atom, right? And there are a couple of ways that we can use to represent the electron configuration. So one way is by using what is called the SPDF notation, which I'm quite sure you're familiar with from your intro or high school chemistry. Basically, it's summarized looking like this, where this number here represents the shell number. So this basically is telling you that the orbital here is in n equal 1 in terms of the shell. The S here, of course, would represent the subshell, where the L value is equal to 0. And then this 2 here, written as a superscript, represents the number of electrons in that particular subshell. So basically, what this tells you is that in the first shell, the S orbital in the first shell is occupied by 2 electrons, all right? So we can use that kind of notation to determine the electron configuration of an atom. Once you know the number of electrons, which of course you can easily determine based on the atomic number, then you can determine the electron configuration using that. Another way of expressing the electron configuration is by using what is called an orbital box diagram. Now this one is a bit more descriptive because not only does it tell you how the electrons are distributed among the orbitals, but it also tells you the direction of spins of the electrons that are occupied in different orbitals, right? And one thing you'll notice here is that 2 electrons, well, let me just say this. So the arrows represents the different spins. Remember, electrons can only have 2 spin quantum numbers, plus half or minus half, all right? So the convention that is accepted in terms of representing the electron spin here is that the arrow pointing up represents the electron spinning, which has a spin quantum number of plus half, and the electron pointing down, or the arrow pointing down represents the electron, which has a spin quantum number of minus half, right? And you'll notice that within each orbital that has 2 electrons, the electrons are spinning in opposite direction, right? This is as a result of what is called the Pauli exclusion principle, which we're going to see later on, which talks about the fact that any 2 electrons occupying the same orbital must be spinning in opposite directions. And there's an explanation for that that's rooted in physics, which I won't get into right now, all right? So basically, this is the orbital diagram for the nitrogen atom. And basically what this is telling you is that you have 2 electrons in the first orbital, the 1s orbital, 2 electrons in the 2s orbital and 3 electrons in the 2p orbitals, and each of these p orbitals are occupied by 1 electron, and the electrons are spinning in the same direction. If I were to use the SPDF notation to represent this, then it would be 1s2, 2s2, 2p3, right? So this would be the SPDF notation, right? And this would be the orbital diagram notation, all right? So these are two different ways that you can represent the electron configuration. And which way you use is dependent on, what you need it for, right? If you don't need to know how the electrons are spinning, then you can simply use this. But if you need to show, or if you need to find out if the electrons will be spinning in one direction or another, then you would use the electron or orbital box diagram to represent that. Okay, so that's as far as electron configurations are concerned, at least in terms of being introduced to it. But there are some rules, of course, when it comes to determining the electron configuration for the ground state atom. And if you remember, we said that ground state represents the lowest or the most stable energy state of anything really, but in this case, we're talking about an atom, right? So there are a couple of things that you need to keep in mind when you're trying to determine the electron configuration of an atom. The first of which is, listed here, is that electrons will simply go into the orbitals of the lowest energy available, right? That's the first thing, right? So if you have, let's say, carbon, which has a total of 6 electrons that you have to assign, the first electron will go into the lowest orbital, and you actually add electrons accordingly, starting from the lowest, all right? Pauli exclusion principle, which I made reference to earlier, you have to make sure that that is obeyed. And as I said before, what this principle says, there are several ways of expressing it. If you look in different textbooks, you'll see different wording, but they basically say the same thing. Basically, what it says is that any atomic orbital cannot accommodate more than 2 electrons. And if it does have 2 electrons in that orbital, those 2 electrons must be spinning in the opposite direction. So you cannot have 2 electrons spinning in the same directions and occupying the same orbital at the same time, all right? So that's what Pauli's exclusion principle is saying. And there's another way of expressing it right here. No 2 electrons in the same atom may have all 4 quantum numbers alike. So that's just another way of expressing Pauli's exclusion principle, which must be obeyed when you're trying to determine the electron configuration of the atom. Okay, another rule that you need to be aware of. It says here, of a group of orbitals of identical energy, electrons will enter the empty orbitals whenever possible, right? So for example, if you have 3 p orbitals, let's say I'm using the orbital box diagram, right? So let's say these represents your 2p orbitals, or they could be 3p orbitals, right? And you have electrons to assign to this. Let's say you're assigning 3 electrons to these orbitals. The first electron will go here, the next electron will go into another empty orbital, and then the third electron will go into the third empty orbital. So that will be the most stable arrangement. You try to spread them out among the orbitals of equal energy. All right. Now, if you have something like this is possible, where you can have, let's say, 2 electrons in this orbital and 1 electron in that orbital. That is possible, but that would not be the most stable. You see what I'm saying? It's possible for you to have 2 electrons in this p orbital here and this empty, but that would not be the most stable arrangement. The most stable arrangement would be this, where the 3 electrons are evenly distributed among the 3 orbitals of equal energy. So that is something that you need to be aware of. Okay.
How do you know which way to point the arrows?
Well, it doesn't matter really, as long as the arrows are pointing in the same direction if they're distributed evenly. And then if you're pairing them up, then the electrons occupying joining another electron will have to be spinning in the opposite direction according to Pauli's exclusion principle. So you made me jump to the next rule right here, because what I just mentioned, that the electrons that are spread among the same orbitals must have parallel spins. They must be spinning in the same direction if you're adding electrons to a set of orbitals of equal energy, right? That's a more stable arrangement, right? Again, it is possible, for example, you can have this. you can have this, this, and this spinning in opposite direction. But again, that would not be the most stable. See what I'm saying? The most stable would be, as I said here, all the electrons are spinning in the same direction for the orbitals of equal energy. Okay, so those are the rules for the ground state configuration, the most stable configuration of the atom, all right? Okay, and later on, we're going to talk about ions as well, all right? These are a bit different slightly when it comes to the electronic configuration of ions. But for now, we're going to focus on atoms. Now, remember I said that, when it comes to higher energy shells, things become a bit confusing because of overlap of orbitals. You have orbitals from a lower, from a higher energy shell, ending up having a lower energy compared to the orbital of a lower energy shell, right? So it becomes difficult to predict the order of the energies of the orbital. But somebody, I don't know who this person was, came up with this diagram, which helps you to determine the orbital order in terms of their energies, right? So basically, when I was a student, the way I remember this diagram, and you need to know this diagram, the way I remember this diagram is that I'll take a sheet of paper and I would write 1s, 2s, 3s, all the way down to 7s here. And then I'll start at the second shell here and write down 2p, 3p, 4p, all the way down to 7p. And then I'll start at the third shell here, 3d, 4d, 5d, 6d. And you can also continue to 7d here, even though it's not shown. And then the next shell will be the fourth shell, where I start 4f, 5f, 6f, and so on, right? And then I draw the arrows that show, right? And basically, if you follow the arrows from tail to head, that gives you the orders of the orbitals in terms of their energies, right? So the first lowest energy orbital will be the 1s orbital. In fact, I think I have it here, right? So 1s here, and then 2s, and then 2p, 3s, and then 3p, 4s, and then 3d, 4p, 5s, and so on. So basically, just follow all the arrows from tail to head, and that gives you the order of the orbitals in terms of their energies. And then based on that, you can determine the electron configuration by adding the electrons to the orbitals as needed, all right? Now, it says here, subshells that are far away from nucleus may exhibit some exceptions to this order, but that would be outside of our scope as far as this course is concerned, all right? So, let's talk about the Aufbau principle, because this is where you're going to see how the electrons are distributed. So Aufbau, I think it's a German term or word, which basically means building up. And this is basically the principle of building up an atom in terms of the electron configuration, and which of course is based on the atomic number, all right? So if you talk about the first element, hydrogen, which has only one electron, the electron configuration will simply be 1s1, right? Because remember, in the ground state, the electron will go straight into the lowest energy orbit. And then the next atom is helium, which has an atomic number of 2. So therefore, to get from hydrogen to helium, you have to add one electron to the structure for the hydrogen. And because each orbital can have a maximum of 2 electrons, that means that the next electron will go into the 1s orbital, all right? And therefore, the electron configuration of helium is 1s2. Now remember, electrons that are paired up in the same orbital will have different spins. So I'm just going to use a diagram here. I'm going to use the orbital diagram to show the distribution. So this is the 1s orbital. I'm just going to put 1s here. So this is hydrogen. In the case of helium, there are 2 electrons. So therefore, one will be spinning up and one will be spinning down. All right. And then the next element is lithium. Now, in the case of lithium, to get from helium to lithium, we have to add 1 electron. Now, that 1 electron that is added cannot go into the 1s orbital because the 1s orbital is completely full, right? So if I were to draw the orbital diagram for the lithium atom, you're going to have 2 electrons here in the 1s orbital, and then in the 2s orbital, which is the next higher orbital, you're going to have 1 electron, which will be spinning either up or down, it doesn't matter, right? So that would be the electronic configuration of lithium, all right? And then to get from lithium to the next element, where the atomic number is equal to 4, after lithium, you have beryllium. So what do you think the electronic configuration of beryllium is? If you follow the trend.
Up, down, up, down.
Well, I'm talking about the SPDF notation. And then we'll deal with the orbital diagram. What would be the electronic configuration? You're gonna start with 1s2, and then what?
2s2.
2s2, all right, very good. And then, in terms of what you're referring to, the diagram, you're gonna have this distribution. 2 electrons in each orbital spinning in opposite direction, all right? Okay, so that's basically how you go from one atom to the next in terms of determining the electronic configuration. Now, as you can imagine, as you continue, for more complex atoms like zinc or cadmium or mercury, you're going to get a long string of characters representing the electronic configuration. And in some cases, that is not necessary for whatever your purpose may be. So that brings us to what we call the noble gas core abbreviation, right? Which is a way of abbreviating the electronic configuration into something more useful depending on the purpose, right? So what we do in determining the noble gas configuration, determining the noble gas core abbreviation, what we do is replace that portion that corresponds to the electron configuration of a noble gas, and I should say here, I should correct this here slightly. I would say of a preceding noble gas, meaning the noble gas that appears before it in the periodic table, with a bracketed symbol for that noble gas, and then you write down the rest of the electronic configuration. So I think I have some examples here. So let's say you're asked, even though it doesn't make much of a difference in this example, but let's say you're asked to write down the abbreviated configuration for lithium, right? So instead of the full configuration like what we did earlier, you want the abbreviated version. According to what I said here, what you do first is identify that portion of the electronic configuration that has the same configuration as the preceding noble gas or noble element. The preceding noble element before lithium is helium, right? And helium has this electronic configuration, 1s2. So what we do in the case of lithium is replace the 1s2 with the symbol of helium within square parentheses, and then we write down the remaining, which would be 2s1. So this here would represent the abbreviated version, while this here would be the standard representation of the electronic configuration of lithium. Now, admittedly, not much of a difference in terms of the number of characters, but it does make a difference when it comes to heavier elements, like in the case of titanium, right? If I were to write down the full electronic configuration of titanium, it is going to be, where should I write it? Let me do it here. 1s2, 2s2, 2p6, titanium is what, 22. So that's 2p6, 3s2, 3p6, 4s2, and then 3d2. This would be the full electron configuration of titanium, right? Now, if I were to determine the abbreviated version, then I would identify this part of the electron configuration, which would be the same as the electronic configuration of the preceding element, which is argon. Argon has an atomic number of 18, so therefore, this part here would be the part which is identical to the electronic configuration of argon. And therefore, I would replace all of that with argon in square parentheses, and then I'll write down the rest, which is 4s2, 3d2, and that would be the abbreviated version of the configuration of titanium. So obviously, in this particular case, you can see a difference between the abbreviated version and the standard configuration of titanium. All right. Okay. Any questions about this? Any questions? Any questions? No questions?
Are we gonna get the electron chart when it comes to testing?
No, you have to remember that. And if you remember what I said, you know, you write a 1s, 2s all the way down to, what was it, 7s, and then you start at the second shell, 2p, 3p, and so on and so forth. Okay, any other questions? How about you guys out there in Zoom? Any questions? Any questions?
Is the electron value of 4s2 just one electron? Because you said argon is 18 and titanium is 22 electrons total.
Yeah, so argon is 18. If you count up this part here, Hold on a minute.
Yeah, is D worth 3 electrons? So like the 4s2 would be 1 and the 3d2 would be 3
If
electrons.
you count up, the total number of electrons. What's wrong with that? Oh, okay. If you count up the number of electrons here within argon, the argon part of the structure, that would be 18, right? And then you have 20, which would be the 2 electrons here from the 4s subshell, and then 22, which would be the 2 electrons from the 3d subshell. So the total count is 22.
Okay.
All right.
The superscript is the number of electrons, the 4
Right,
and the 3 is just the location.
Exactly. The superscript represents the number of electrons within each orbital.
Okay.
All right. Okay, any other question? Any other questions? Okay, so let me see what's next. Okay, so let's see if we can collectively do this example. It says write the electronic configurations for sulfur using both the SPDF notation and an orbital diagram, right? And I'm assuming they're asking for the full, not the abbreviated configuration, right? So the first thing you will do is what?
Draw your diagram.
No, you have to, well, yeah, that too, but I would look up
That's
the
what I was-
atomic number of sulfur, right? Which is 16, right? Yeah, so 16 would be the atomic number of sulfur, right? So yes, you're right. Draw the diagram, and that diagram, of course, you're going to use as your guide to show the orbital order. So the first orbital would be 1s, that would have 2. 2p would be I'm sorry, not 2p, 2s.
It's a box that draws it down.
Yeah. 2s would be 2. And then 2p would be 6, right? So far we have assigned 10 electrons. Then the next would be 3s, which would be 2, and then 3p will be what? So that's 12 plus 4. So that would be the electronic configuration, the SPDF notation for sulfur, right? Now, in terms of the orbital diagram, it's going to look like this. The 1s will have 2 electrons spinning in opposite directions. The 2s will have 2 electrons spinning in opposite directions. Then you're going to have the, so this is 2s. And then you're going to have the 2p's, and there are 3 of them. One, 2, 3, then 4, 5, 6, right? So that's 2p. And then 3s, there's only 1 of them. And of course, 2 electrons will go there. And then now we get to the 3p. So let me hear what you have to say about this is 3s. And remember now, the 3p's, there are 3 p orbitals, and there are 4 of them that you have to distribute between them. So how do you think those electrons will be distributed?
2 in the first box.
2 in the first one, oops, 2 in the first,
Point the other 2, or 1 in each of the boxes.
exactly. And that would be the orbital diagram representing the electronic configuration of sulfur. All right. Now let me ask you one more question, even though it's not asked here. So let's say you're asked to write down the abbreviated version of this. How would you determine that? The abbreviated. I'm sorry?
It'd be argon.
Argon, you sure? Remember, it's the
Oh,
noble
shit.
gas that comes before.
Neon.
Okay,
Sorry.
so what's the electronic configuration of neon? It's going to be this right here. Right, because neon has an atomic number of 10. 6 plus 4, 10. So the abbreviated version would be this. Right? And that's how that is done. All right, any question?
So when it gets to like the test and the assignment, it's gonna tell us what we should use, like a.
Right, the question would have to be kind of specific, like the question could ask you, what's the, like, in the assignment question, I'm gonna give you now, for example. Oh, here it is. Part is asking for the unabbreviated electron configuration, so that's the full. And then the next question says the abbreviated version, which is what we just did. All right, so, you know, yeah, that's what the question will have to be worse. All right, okay, any other questions? Any other questions? Well, let me see if there's anything else. Okay, so let me give you this right now, actually.
There a assignment Dropbox for chapter 7 yet?
I think I created one this morning. Yeah. Okay, so let me give you this right now. All right, so, and for you guys out there in Zoom, let me publish assignment number 8 right now. You get out of this. And go to this. And go here, go with that. Assignment number 2. Okay, so let me publish this right now. Okay, so this is assignment 8, I'm downloading right now. Okay, so, like I said, you need to, you know, remember that diagram, but of course I wouldn't expect you to memorize that now, but, you can bring it up on your devices, whatever you have. So that you can, do these, so let me help you with the first couple of them. So the question is asking for you to write an unabbreviated version of the configuration of these atoms, starting with sodium. All right, so let me hear what you have for me in terms of what the electronic configuration is for sodium. What's your atomic number of sodium? 11, okay, very good. And then what? So the first orbital is 1s, right?
That's 2.
Okay, what's the next orbital?
Just
2s, which would have 2. What's the next orbital?
2p,
2p, which would have how many?
6.
And what's the next one?
Yes.
3s, which would have
1.
and that's it. All right, so that's basically how we do sodium. I'm basically going to do the same thing for the others. All right. Okay. Any questions about this one? Any questions? Any questions? All right, let me clear this because I want to do one example of the abbreviated version. So let me clear this and scroll down. Okay, I want us to do. I'm going to start off with cobalt. Okay, so let me scroll down. What's the atomic number of cobalt?
47.
Okay, so the atomic number of cobalt is 27. Okay, so tell me what to write down.
Fe.
What's the first orbital?
It's not the one where you do the proceeding.
Well, you have to do what, okay, maybe I should have said this. What I would do, especially since you're learning this for the first time, I would write down the full configuration first, and then based on that, determine what the abbreviated is. All right, it becomes tricky when you try to just find out what the abbreviated is from the outset, right? So I would do the full first and then look at it to determine what the group 8 element that precedes it will be, and then based on that, determine the abbreviated version. So let's do the full first. So the first orbital will be what? 1s2, right? The next one is 2s2. The next one is 2p6. The next one is 3s.
3s2.
3s2. And the next one is
3p6.
3p6. And then what?
For us to.
four S two, so that's 20, and then, I'm sorry, four S two. And then, so what we have so far is 20, remember it's 27,
So it'd be 3D7.
3D7. Exactly. So that would be the full electronic configuration for Cobalt. Now, to get from here to the abbreviated version, what do we do? Where's Cobalt? Cobalt is there,
So go
so
to
the group A element that
Argon.
comes before it is what?
Argon.
Argon. So argon would be equivalent to all this I'm circling here. Alright? So the actual final answer would be the symbol for argon is square parentheses, and then 4s2, 4s2, 3d7. That would be the abbreviated version, alright? So I would strongly recommend that you do the full electronic configuration first, and then you figure out which group A element that comes before that particular element, and then based on that, you can determine the electronic configuration. All right, so what I want you to do right now is to do the rest of the first problem, the first. Hold on, let me, it's okay for me to clear this? All right, so let me clear this. So I want you to do all of questions 1 through 5 in part A. I want to do the other questions in the rest of the questions here, excepting silver. Silver is a bit different, and I want to discuss that with you guys. But you should be able to do the rest of them. And also, you should be able to do questions 11 through 15 as well, which is actually easier than the others. So I want you to do those now. If you have any questions, feel free to ask.
The reading. See, element, why are we going back so far? Is it like the same element? But that's
Okay,
like-
which one are you talking about?
Just for all the abbreviated, it's like when we just did cobalt,
Mhm.
back to argon.
Yeah,
So
because
that's
argon is the
first
grouping element
gas.
that comes before cobalt. This is cobalt right here.
No, yes,
So it's the first noble gas?
Exactly, the noble
I
gas.
thought it was the first element.
No. The element, the group A element that comes before cobalt in this case. So argon is here, so you're gonna use that in writing down the electron configuration, the abbreviated electron configuration. In the meantime, just so you can do it. Okay, is Brad here? Gerard? I'm sorry, not Gerard, Green? Kennedy? Leonard? Okay. Okay, I think that's it. All right. Yes, sir.
Noble gas column is very outside of here.
Group 8, that's the last column on the right. Or 18, depending on the numbering system.
Okay.
Right. So whenever you do the abbreviated version, once you get the full configuration, you look for that part of the configuration, which is the same as the configuration for the immediately preceding group 8 element. And then that forms the basis for determining the abbreviated version. Yes, ma'am.
So if S goes up to two, he goes up to 6 maximum, just equal 8.
Okay.
I don't know if I'm missing it.
Right, right. I'm glad you asked that question. Remember, folks, the maximum number of electrons that can occupy each orbital is that S can have a maximum of 2, P will have a maximum of 6, D will have a maximum of 10, F will have a maximum of 14. And I don't think you need to go beyond that, right? So S is 2, P is 6, D is 10, F is 14. Those are the maximum numbers.
6 hour read.
I'll be right back.
Yay.
Fun so far? That's what I'm here for.
Sort of, what do you think?
Oh, remember, don't do silver.
Already.
Don't do it yet. We're going to, silver is a bit different among these elements in terms of, the rules, so skip silver, move on to the other one.
Maybe that's four.
You know, when you do the abbreviation, you use AR, what's to stop us from using CA and then putting?
Because the rule, you know, of course, you know that these are guys who set up the rules. The rule is that you have to look at the group eight element that comes before the element that you're working on. Group eight, the last column, the known gas element. So which one are you working on right now? Which one? Oh, Tellura. Okay, so Tellura is T 52, right? So basically what you need to do is figure out what the electronic configuration of Tellurium is, and then identify the part which has the krypton configuration, which is 36. So let me see what you have.
That goes all the way up to 46. So. 36.
Yep. Right. So that would be krypton in square parentheses, and then you write down the rest.
Max electrons on the subscript F minimal 14.
Yeah.
you look at, radium, it's number 88. No, yes.
What?
Never mind.
Rhodium or radium?
Now I figured it out.
Oh, okay.
You're good. Okay, 86 for RN goes all the way up to 66, so.
Or which one? No, that's radar, that's different. Oh, which one, I'm sorry, which question are you doing? Sorry.
9,
No, radium is RA.
yeah, 88.
Oh, right, okay, so radium is 88, so radon would be the. In square parentheses, in the. Abbreviated version, and then you have,
So it's basically just.
1, 2, 3, 4, 5, 6, so it's that 6S2
7 is.
or 7S. Yeah, 7S2, so just the radon symbol in square parentheses and then 7S2, and that's it. Yeah. Yeah, I think it's important, but now, check, the one oh, so after slide S.
Yeah.
Hold on. But according to this, you should have, after 40, you should have 5P.
637.
Oh, but you're stopping at 40, okay. So 46, I know this is 30, 36, 38, yes, so I think this should be 42. Yeah. Okay, so, all right, so in the case of tellurium, where's T? 52. two.
You get, are you from?
Okay, so the group A element accounted for is krypton according to the periodic table, right? So the answer is. There we go. Based on what I see here for you. Burial, krypton, so krypton
Six.
would be in square parentheses. Which is 36, which goes up to here, right? And then the rest, according to what I see here, would be 5s2, 4d10, and then 5p4. And that's it. And you do the same thing, fellas, like in the case of radium, or radium is there, so radium will be 86, and 86 goes up to. So that's 30, 36, 38, 48, 48, and 6, 54, 56. Yeah, okay, yes, it goes up to 66, right? So that means that in the case of radium, it would be Rn. And then 7s2.
Yeah.
That's it.
X is 54.
Later on, yeah, but there's something I have to cover first before we can do the one for silver. At least you'll be doing silver, but I have to cover something first before we get that. Okay, are we finished with questions 1 through 15? Going once, going twice. All right, let me clear this. And let me go back to the PowerPoint. And let me. Okay, so let's talk about the electronic configurations as it relates to the periodic table of elements. Firstly, I want to identify different regions of the periodic table which you may not know about. So there's a difference, for example, between what is called the main group elements and the transition elements, all right? So in terms of where these regions are in the periodic table, the main group elements would be in groups 1A through 8A, all right? So the blue colored boxes here and over on this side represents where the main group elements will be located. And the thing about these elements is that as you go from one element to the next across a period in these regions, you'll find that an electron is being added to either an s or a p orbital of the outermost shell, all right? So that's basically what characterizes those elements located in the main group. Now, the other region here, there are two regions here and also here. these are called transition elements, the elements in these regions. In fact, in this region here, they're called the transition elements, and in this region here, they're called the inner transition elements. And the thing about these elements is that as you go from one element to the next across any period, you're adding an electron to a subshell, which is not on the outermost shell, but an inner shell, all right? So that's the transition region, right? So if you, for example, go from hydrogen to helium, the electronic configuration of hydrogen, as we said before, is 1s1, and the electron configuration of helium is 1s2. So basically, you're adding an electron to get from hydrogen to helium, you're adding an electron to an s orbital. Now, in the case of a transition element, you're going to have titanium here, and the next element is vanadium here, right? Now, if I remember correctly, the electronic configuration, the abbreviated version would be argon for titanium, right? Would be argon, then you have what is it? You have 4s2, 4s2, and 3d2, right? That's titanium. And then the next element is vanadium, for which the electronic configuration will be 4s2 and 3d3. So in this case, going from titanium to vanadium, you're adding an electron to a 3D subshell, which is of a lower energy compared to the fourth subshell here. So you're adding an electron to an inner orbital as you go from titanium to vanadium. And that's true right across the board within that region of the transition and also in a transition element. Okay, so that's as far as that is concerned. Now, to look at this in more detail, you're going to see how the electrons are added to different orbitals in different regions, right? So as I said before, going from one element to the next in any of these regions here, the main group elements, you're adding an electron to either an s or p orbital. So for that reason, this region here, which contains group 1a and 2a, that region is called the s block region, right? So those elements are called the s block elements. This region here is called the p block elements. This region here is called the d block, and this region here is called the f block, right? So those designations are according to whether or not an electron is being added to a particular orbital or particular orbital type as you go from one element to the next across a period within that region. All right. Okay. So here's another question here. Give the complete ground state configuration of strontium atom in the SPDF notation and also in the noble gas notation. So what's the atomic number of strontium? SR 38, right? So the atomic number is 38. So let's deal with the complete configuration first. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. No, actually 3d10. Because remember it's 38. D can have up to 10 electrons. 4p6, 5s2. So that's 30. Okay, so that's correct. Yes, that's indeed the full configuration of strontium. Okay, so what will be the abbreviated version? Now, the element that precedes strontium is. Okay, which strontium we got? I lost it. Oh, okay, so it would be krypton, right? So krypton is 36, so 36 will cover everything up to
4p6.
4p6. So that's
KR in parentheses. Or no, KR.
KR in parentheses. And then
5s2.
5s2. That's it. All right. Okay. So that's how that is done. Any questions? Any questions? All right. Okay, so now we're gonna get to some exception, right, which is the reason why I skipped over silver. In the first question here, right? Now, there are some exceptions at particular regions, especially when it comes to the transition metals. When it comes to the off-bar principle, right? So what I'm gonna do is start with scandium, which is in period 4 of the periodic table, right? So the electronic configuration of scandium, we can use the orbital the box diagram. But basically, the way it's represented here, we put the symbol for argon in parentheses because that's the group 8 element that comes for it. And then we assign an electron to the 3D sublevel and 2 electrons in the 4s sublevel. Now, let me just say here that there is a minor error that we have here in this representation, because what should happen is that these two should be switched. So please make a note of that. The 4s should come before the 3D. All right? And that should be true also here as well. Right? If you look at the order according to the chart I showed you, it's a 4s first, then a 3D. So please make a note of that, right? So with that in mind, this will represent the electronic configuration of scandium. And then to get from scandium to titanium, you add 1 electron to any one of these orbitals, and you're going to end up with this here. To get from titanium to vanadium, you add one electron to any one of these 3, and you end up with this electronic configuration, right? Now, here is where the exception takes place. One would think, based on the trend that we have been using so far, that to get from vanadium to chromium, all we have to do is add 1 electron here, right? But it turns out, and there's some experimental data that shows this, that this would not be the ground state configuration, right, for chromium, right? Instead, what would happen, not only will you have 1 electron being added here, but one of these 2 electrons will be transferred to this orbital right here. So basically, you're going to end up with this subshell being half filled and this 4s subshell being half filled, right? So therefore, this, it turns out, would be the more stable or the most stable ground state configuration of chromium. So as stated here, a half-filled D subshell plus a half-filled S subshell turns out to be slightly lower in energy compared to what you'd expect, which would be 2 electrons in the subshell S and 4 electrons in the D subshell, all right? So that's what happens in the case of chromium, right? Now, we can continue from chromium to determine the electronic configuration of manganese. Let me erase this here and this here. Okay, so to get from here to manganese, we add 1 electron, and that 1 electron will go into the 4s sublevel, because remember, the 4s sublevel is of a lower energy compared to the 3D sublevel. So 1 electron will go there, and then to get from manganese to iron, you add 1 electron here to give you this. Then you add 1 electron to the iron to get cobalt. That electron will go here, and then we add 1 electron to cobalt to get nickel, and that electron will go here. And then now we get to another exception, right? And that is copper, right? Now, again, you'd expect that, okay, to get from nickel to copper, you just add 1 electron here. Turns out that that is not the most stable configuration. Instead, the most stable configuration will have the 1 electron here, but 1 electron here from the 4s sublevel will be transferred to the 3D sublevel, right? So here we have a situation where the 3D sublevel is completely filled and the 4s sublevel is half filled. And as stated here, it turns out, again, this was determined by experiment, that the half filled D sublevel plus the half filled S sublevel have a lower energy compared to the 4s2 and the 3D9. That's almost time. Oh, it is time. Okay. So let me just finish up this and then we'll call it today. So basically, when you get to the situation where the 3D sublevel is completely filled and the 4s sublevel is half filled, then basically that will be more stable than the alternative, right? So with that said, you should now be able to determine the electronic configuration for the one that we skipped, number 7, silver. So I'm going to leave that for you to look at. If you have any questions, feel free to contact me, all right? Okay, so that's it for today. And I'll see you guys on Thursday. Yes, sir.
Last Tuesday, did you find a calculator in the lab at all?
Probably should ask security, because sometimes the lady would come to and walk to the. Yeah. Okay, so you guys out there in Zoom, I'm signing off now.